Hello everybody, my name is Willy from Lancaster University in the UK. In this video, I will present you performance optimization on big little architectures, a memory latency error approach, a work accepted in LCTES 2020. This work was partially sponsored by ARM in Manchester. Today, because CPU can't go faster because of power consumption and related heat problems, the trend is to multiply CPU cores and packages to keep increasing performance. However, on some use cases, performance is not required at all times. For instance, on smartphone and embedded systems, some activities like emailing does not really need powerful CPU. On the other hand, playing video games and browsing dynamic websites, performance is appreciable. To accommodate these different kinds of workloads, modern architectures involves a mix of different CPU types. Such architectures use energy-efficient CPU for lightweight workload and add powerful CPU but more power-hungry for heavier workload in a multiprocessing fashion. For instance, ARM Big Little or the future Intel Lakefield use this kind of design. The challenge is to use efficiently this hardware and to task map correctly the workload depending on its requirements. As an example, this is a schematic of such an architecture found in the Samsung Galaxy S5. As we can see, we have two CPUs, one energy efficient, named a little, that implements an ARM Cortex-A7, and a performant one, named a big CPU, that implements an ARM Cortex-A15. The CPUs form an asymmetric multiprocessing architecture, or AMP, in the same way as SMP. In this kind of system, the two CPUs are connected together via an interconnect which takes the responsibility of managing the data coherency between the two CPUs. This talk discusses an interesting issue found on a particular interconnect related to extra latency induced by data coherency. During this talk, we will first try some experimentation to show the problem on real-world application. We will then dive in hardware architectural details to understand what is going on precisely. Next step, we will model the problem and then use this model at runtime to avoid it. We will then evaluate our solution with different workloads and conclude this talk. Let's get started. Okay, first, let's have fun and try to run GCC from the spec benchmark suite on the big cluster, while keeping the little cluster in idle. We note that the values are an average time of 5 runs. On the figure, the right bar shows the execution when both clusters are set up to run at the highest frequencies. Here, GCC finishes its work in 200 seconds. Now, assuming we want to save energy and we set up the frequency of the little cluster, which is not used except for the OS services, the results are shown on the left bar. Curiously, we have a slowdown and GCC finishes 50 seconds later. That is surprising and is not really cool. Okay, for curiosity, what is the situation if we run GCC on the little cluster while keeping the big in idle? Let's have a try. It's even worse. To save energy, forcing the frequency of the idle cluster almost double the time for finishing the workload, even if the hardware is not really used for hours. Really not cool. This shows that there could be a serious problem for performance while thinking of saving energy by simply reducing the frequency of the non-used cluster. Let's have a look on another application. We'll use povray from the same benchmark suite. As we can see, there is no extra delay when running on the big cluster while the little cluster is idle. And it is the same when we swap the role. To summarize this experiment, it seems that there is an extra latency that could depend on the workload. But what is the problem exactly? In fact, the culprit is the memory behavior. Here, in green, I show the performance metric counter extracted with the nuxperf tool. This value is the total sum of memory accesses divided by the number of CPU cycles for the full execution of the workload. As we can see, GCC have quite a lot of memory accesses, while povray has quasi none. In fact, the compiler GCC here is doing some source code optimization and internally uses graph data structure to represent the code to optimize, and as such have mostly random memory access and suffer from a lot of cache misses. On the other hand, povray is a ray tracer and works mostly linearly on flat images, and the CPU memory prefetcher can help a lot. These examples show that depending on the workload's memory behavior, CPU frequencies configuration are really important, even if we don't have any particular active workload on the idle cluster other than OS services. If we do not take care of this, we could have serious slowdown on our workload. On these particular examples, GCC could have a 50% slowdown on the little cluster and 30% slowdown on the big cluster, while povray has no singular slowdown. So, why this? Let's have a look on some details in the hardware. Here I show again a schematic of the architecture. Let's imagine that a core from the little cluster wants to access a particular memory. If the data is not already there, it will look in its CPU core private L1 cache. If this private cache does not have the memory, it will then check in all other private L1 cache of the other cores within the same cluster, and also in the shared L2 cache. Imagine that this memory is not present at all in the cluster. It will require to access the main memory. To do so, the request is forwarded to the Cache Coherent Interconnect, or CCI, to fetch this data. To ensure data coherency, the CCI will have to check if the memory is not currently in any devices that are present in the coherency domain, here the big cluster, by performing a snoop request. The problem that we see earlier is that the snoop acknowledgement is dependent on the frequency of the targeted CPU. If the frequency of the CPU is too slow, then an extra delay will appear that we call snooping latency. It is likely because of this mechanism that GCC have poor performance when the idle cluster is set to a low frequency in order to save energy. On some interconnect design, in order to avoid this snooping, it is possible to simply store which memory is present in the different clusters at the interconnect level instead of snooping the cluster, which is called a snoop filter. However, the particular hardware that we use does not have one. This talk proposes a software solution only to take care of this snooping latency. Then, if the memory is present in any cache of this cluster, there is a snoop hit and the memory is fetched from this cluster to the other one. If not, there is a snoop miss and the memory is fetched from the main memory. Now, with this in mind, how could we take care of this information to avoid this snooping latency? Let's try to model it. To do so, we'll use a simple microbenchmark that is doing only memory accesses by doing pointer chasing in a simple loop. Here, the code is accessing an array to fetch the next index to follow in the same array. The game is to arrange the indices in the array such as to cover different pattern access and try to touch each level of the memory hierarchy. We note that this benchmark is compiled with loop and roll optimization to maximize the amount of memory operations during its execution. We first fix the array as to access the array purely sequentially with a stride of 1. On a different run, we fix this array to do some jump in the memory, but still showing a linear pattern. The CPU memory prefetcher could still work elegantly. As to cut effectiveness of this prefetcher and force a memory access, we arrange the array to have a random pattern. Let's have a look on the results. Here, the first number in the legend is the size of the array, and the second one is a stride used to access the array. 1 means we access directly the next index. The x-axis here is the set of frequency used. For this experiment, we keep the big cluster at its highest frequency, while scanning each frequency of the little cluster, from 200 MHz to 1.4 GHz. The memory frequency is shown just for completeness. As we can see, when we access the big cluster while the array fit in the L1 cache, we have a latency of 4 CPU cycles. When we increase the size of the array to touch the L2 cache, we increase the latency to about 5 to 6 cycles. As we have a purely linear pattern, the prefetcher is smart enough to prefetch the memory and not incur more latency when we touch RAM memory. Changing pattern with sequential stride of 16, we are still fine in L1 cache, but as we keep increasing and touch the L2 cache, the latency is greatly increased but still nothing to notice. However, when we touch the main memory, we're starting to see some extra latency with low frequency on the idle cluster because of the snoop mechanism. Here we can see that we could have 50% slowdown from the highest frequency to the lowest frequency. The random pattern shows the same behavior when we start touching RAM. We can clearly see that there is an extra latency when we try to reduce the frequency of the idle cluster, here the little. Here I show the rate of memory box access during the runtime. As we can see, when we have slowdown with low frequencies, the memory access rate is also reduced, due to an increase in snooping latency. So, with this in mind, how could we detect when we have snooping latency? In fact, the CCI have some performance counters that could be useful. Precisely, it provides a number of stalling cycles and number of read requests amongst others. Here, I show the number of stalling cycles per read request. As we can see, when we start having timing issue, these values are increasing. We also see that the increase in timing is not a direct linear relation with the amount of stalling cycles. The reason is that this metric from the CCI does not only account for our benchmark, but account for the full cluster with all other applications running on the system, whereas CPU cycles and memory accesses are for the benchmark only. The situation is the same for the little cluster. Now that we have a mean to detect when we have a snooping latency, we can produce a model that can suggest when we need to increase the frequency of the idle cluster in order to avoid this snooping latency. To achieve this, we use a simple decision tree. This decision tree simply describes that when we reach a certain threshold at the CCI level, and with some amount of memory accesses at the CPU level from the particular application we want to optimize, we should increase the frequency of the idle cluster in order to limit the snooping latency. So, now that we have a model, let's use it. Under Linux, the kernel uses dynamic voltage and frequency scaling to manage CPU frequencies. We have implemented our approach on top of the on-demand governor, which is a standard governor used on many Linux distributions. This governor uses a load metric which describes how the CPU is busy. Basically, when the CPU is mostly doing nothing, the governor shows us a low frequency. And when the CPU is starting doing something, the frequency is increased to satisfy the performance demand within the CPU frequency capability. We note that the load metric does not take into account any information about characteristics of the activity such as memory accesses. Here, I present our modification to this governor that takes into account memory access made by the application and memory stalling information at the CCI level. Modifications are highlighted in red. Basically, read PMCs from the CPU for every application that are running and also cluster-wide information from the CCI to check if the memory is not stalling during snooping operation. If we detect any snooping latency, we suggest to increase the frequency or to decrease it otherwise. We also keep the calculation of the on-demand governor and then we simply pick up the highest frequency suggested by both approaches within the available frequencies. So, how do we succeed to avoid snooping latency? Let's have a look. First of all, we've tested this approach on the microbenchmark. These figures show 3 comparatives against the default on-demand governor, which is our baseline highlighted in red. The first 2 comparators are forcing the idle cluster to its highest frequency or its lowest frequency to check what is the maximum and the lowest possible speedup or slowdown of the workload. Then we have our new anti-snoop governor. As we can see, when the RS fits perfectly inside the CPU cache, there is no memory access and hence no snooping problem, shown by both maximal and minimal frequency comparator. Also, our new governor performs the same. This means that our approach doesn't really incur much overhead when it's not useful, even if we keep reading the different PMCs. I'm glad this is a video. And I will not dive into the data and will forward you to the paper where we describe and adjust correctly these results. But basically, the key point is that we are not performing the best compared to when we use the highest frequency, but this approach performs quite nicely with a 1.4 to 1.8x speedup against the simple on-demand. On the set of real workload, our approach performs quite nicely too, with a speedup as up to 1.4x against the on-demand governor. To conclude this talk, I presented you a software solution to the snooping latency problem that are present in some AMP or SMP architecture. There exists a hardware solution to the snooping latency problem by using a snoop filter. However, there is still quite a lot of hardware that rely on interconnects that doesn't have one. We have implemented our approach directly in the Linux kernel, and kernel patches are released as open source. We note that even if we are continuously reading PMCs and consume a bit of memory space for each processes, the overhead is far absorbed by the gain of this approach with a 30% speedup against the default on-demand governor. Thanks for watching.